The standard deviation is a little bit more difficult to find the confidence interval for, or not even difficult, but it works in a very different way. The mean, whether the sample was large or small, both worked off of a bell-shaped curve that was symmetric, and then the proportions also worked off of the normal distribution, which was again symmetric. The distribution that we need for the confidence interval for the standard deviation is unique because it's not symmetric, and that means that it's going to be a little bit more work, and we're going to have to approach it just a little bit differently in order to get the confidence interval. Now, first of all, the idea is that, as with the mean, we use the sample standard deviation as a point estimate for the population standard deviation. So remember, the sample standard deviation is represented by the variable s. Excuse me. And the population standard deviation is represented by the Greek equivalent of the letter S, which is sigma. Now, there's another value, another statistic that is not discussed as often because its interpretation is not as clean as the standard deviation's interpretation, which is a phrase that most people never thought they would ever hear or say. But the last step of calculating the standard deviation, after you go through all of the many steps of calculating it, the last step is to actually take the square root. Right before you take the square root, you get a value called the variance. It is the value that you have right before you take the square root in order to get the standard deviation. Now, the reason why the variance is worth actually talking about is that the standard deviation, because of the square root that's involved with it, that square root actually makes it a bit harder to work with. So what we actually do is we base a lot of what we do for the standard deviation off of the variance. So the variance does not conform to a normal distribution the way the mean would, or the way the proportion would. If we were to do a sampling distribution for the variance, what we would get is actually not a bell-shaped curve. And a good part of that is because the squaring means we always have a positive result. Unlike a normal distribution where we can have values that fall below the mean and therefore have a negative z-score, the test statistic for the sample variance is always going to be positive because of the squaring. Excuse me. So if the random variable x has a normal distribution, so we get that same kind of underlying assumption that we get when we did the proportions as well, that the underlying values that we're dealing with are normally distributed, or at least pretty close to it. then if we were to take the sample size minus 1, that should be a familiar thing, and yes, degrees of freedom are going to figure into this, times the sample variance over the population variance, this gives us a random variable that we refer to as chi squared, a Greek letter that kind of looks like a script X squared. So it's, if we attempt to apply an American or an English spelling to it, we write CHI. It's pronounced chi, or actually probably more accurately, it's pronounced key. But the American version is we just say chi. This chi-squared distribution is what we're going to be using to get our critical values for a confidence interval for the variance or standard deviation. So let's take a look at what the chi-squared distribution actually looks like. Well, first of all, it is a family of distributions. Like the t-distribution, this is going to be determined by the degrees of freedom. And just like with the t-distribution, the degrees of freedom is n minus 1. They use the variable k in this graphic. The idea is that this does not form a bell-shaped curve. It has a similar kind of peaking, as you can see here. In the blue curve, it peaks narrowly and very early on. In the red, it peaks lower and it has a more gradual climb and descension from the peak. And then if you look at the green one actually is kind of almost getting towards what a normal distribution might look like, almost. But the idea is that these all have a basic kind of bell-shaped curve, whether it's tall and narrow or flatter and wider, but they all have a thicker tail on the right than they do on the left. In fact, if you look at the blue curve, it doesn't seem to have much of a tail at all on the left, but it has definitely a thin tail going out to the right. These are all skewed to the right. All of the chi-squared distributions are skewed to the right. The idea is that the higher the sample size go, the chi-squared distribution will move in the direction such that it will eventually have something like a symmetric bell curve, but it never entirely gets there. Another thing to note here is that, again, as I mentioned, because of the squaring, all of the values for this are positive or at least 0. So that's something that's different, again, from the normal distribution or the t-distribution. So again, the idea is that at low sample sizes, we get something that departs greatly from what a normal distribution would look like, just like with the t-distribution. The smaller the sample size, the greater this departs from what a normal distribution should be. And then the higher the sample size gets, we see that departure gradually shrinking until if we get to a large enough sample size, we get something that is close to normal, but not exactly. So here's really one of the big interesting things about this, is that because it's not a symmetric curve, we have to find the critical value for the left side of the confidence interval and the critical value for the right side of the confidence interval separately, because they're not going to be the same values. The whole idea of the standard normal curve or the t-distribution is that they're centered on z equals 0 or t equals 0. This is not centered on 0. All of the chi-squared values are greater than or equal to 0. Because of that, since the curve is not symmetric about 0, the left and right side critical values will not be symmetric and need to be determined separately. So the way that we're going to determine the left and right side critical values is going to, as before, be based on the confidence level, and therefore the area in the middle as well as the area in the tails. So the calculator does not have the ability to do this. There are chi-squared calculators out there in the world, but the graphing calculator does not have the capacity to do this. Suffice to say, the higher level math behind finding the areas under the curve and then turning that around and doing an inverse chi-square distribution is incredibly complex. So much so that, and the need for it being relatively little enough that it's not worth the effort to program it into the graphing calculator. More advanced calculators do have the capability. There are websites that have chi-squared calculators in them. We will be largely using a table. So for all of our problems, I'll be referencing this table. So the idea is, again, for some confidence level, let's take, for example, a confidence level of 90%. That means that we're looking at an alpha of 0.10, and therefore an alpha over 2 of 0.05. So what we've got is, we're going to draw a generic chi-squared curve, which is going to have, coming out of basically the origin, it's going to have a gradual, it's going to have a little bit of a gradual curve upward, a big hump, and then a steep curve upward, and then a gradual curve downward. So, like with the bell-shaped curve of the normal distribution or the t-distribution, we're still looking at having the area in the middle be equal to our 90% confidence level, and the area in each tail then being equal to alpha over 2, so that the total area underneath the whole curve is 1. Nothing new there. Nothing new there. Now, the chi-squared table works differently from the normal distribution or a t table, because this one deals with area to the right. That's really important. It is area to the right of the critical value. So we have two different critical values to find. Excuse me. Got to switch back to the pen there. The chi-squared value to the left, or the lower bound, and the chi-squared value to the right, or sometimes this is written as chi-squared sub u for upper bound. Now, again, these deal with area to the right. So to get chi-squared sub r, or chi-squared sub u, we need to have our confidence level, excuse me, we don't want that equal, we want it just to say area to the right or left. The confidence level is 0.90, and the area in each tail is 0.05, so the area to the right of this is simply 0.05. That means that we're going to be looking at this column here. That's where we're going to get our chi-squared sub r, or chi-squared sub u. As for chi-squared sub l, that's got to have the full 90% in the middle for our confidence level, plus the 0.05 to the right. That means that we're looking at 0.95 as our area to the right. So we'd be looking in this column for chi-squared sub l. Now, as for what our critical values are, that's going to be determined by our degrees of freedom. So we also, in dealing with this, need to know our sample size. So suppose, for just this example here, suppose that we're told the sample size is 10, which means the degrees of freedom is therefore 9. Then we would be looking in, we would be looking in this row here. And we can see from the intersections then what our critical values would be. This 3.325 is going to be our chi-squared sub l. So I'm just making a big mess of this. And this over here, the 16.919, is going to be our chi-squared sub u, or sub r. So again, L for left or lower, and then either R for right or U for upper. Either way you want to label it. The fact of the matter is those are our critical values. So let's take a look at another example here where we can use the table again. So we're told, in this case, we're not doing a full confidence interval. We're simply determining the critical values for a 98% confidence interval when the sample size is 16. So if the sample size is 16, from that we can get the degrees of freedom, which is 15. We also are told the confidence level here is 98%, or 0.98. That means that alpha is the remaining 0.02, and that means that the area in each tail is split up into 0.01. So we again are going to just sketch out a chi-squared distribution with a steep rise on the left side and then a more gradual falling tail on the right side. And here will be our chi-squared sub L with an area underneath the curve to the left of 0.01. We have our 0.98 in the middle. And then our chi-squared sub U. I'm going to stick with the U here because in the homework assignment, that's what you're going to see is chi-squared sub U. And that has in its tail the other 0.01. So that altogether we have the full 0.98 in the middle, 0.01 to each side. So altogether we have the total area of 1. So for chi-squared sub L, the total area to the right is the 0.98 plus the 0.01 is 0.99 for the area to the right. For chi-squared sub U, the area to the right is simply the 0.01 in the right tail. So we've got our degrees of freedom is 15. We've got our areas to the right are 0.99 and 0.01. So we're going to flip back over to that table. And find the columns we need and the degrees of freedom we need. So the degrees of freedom was 15. That puts us in this row down here. And our areas to the right were 0.99 to the right. That's for our chi-squared sub L. And 0.01 to the right for our chi-squared sub R. Which means 5.229 is our left critical value, and 30.578 is our right critical value. Again, there is no symmetry to be looked at between these two values. You know, they are what they are. They come from this table, and somebody did the work and hashed it all out for us, and we just have to use the table appropriately. So our left critical value is 5.229. Excuse me. And our right critical value then is, from the other side, 30.578. Now, as for the confidence interval, this is, again, unique among the other sections in this unit in that we don't actually have to calculate a margin of error, which kind of goes with the idea that this isn't symmetric to begin with. You know, the idea for the margin of error was if you had the value of E, you add it and subtract it, because the interval was going to be symmetric about your point estimate because the distribution you were basing it off of is symmetric. This distribution is not symmetric. So we actually are not going to be calculating a margin of error at any point. We're going to go right to the left bound and right boundary of our confidence interval. the confidence interval here let me just stick another page in here before we get onto an example. The confidence intervals for s squared and s. Now, we're not actually going to be interested in the confidence interval for s squared, but again, we start with that because it's based off of the standard. This standard deviation comes from the variance. The confidence interval is going to be n minus 1 times s squared over chi squared sub u is less than sigma squared, which is less than n minus 1 times s squared over chi squared sub l. Now, yes, I did put chi squared sub u in the denominator of the value on the left and chi squared sub l in the denominator of the value on the right. I will address that in a moment. One other thing I want to do here, though, is say that if we want an actual confidence interval for the standard deviation, not the variance, well, we just need to square root all of this. So we put a square root over the n minus 1 times s squared over chi squared sub u is less than the standard deviation is less than the square root of n minus 1 times s squared over chi squared sub l. Now, where did these fractions come from? Well, they came from the idea that chi squared is the test statistic of this form, but the form that this is written in is based on knowing both the population variance and the sample variance. We don't know the population variance. We're trying to estimate it. So what we do is we solve this to get sigma squared. And the way that works then is we, as we've done before, we would flip these upside down to get sigma squared in the top. And then we would multiply top and or both sides rather by n minus 1 times s squared to get that out of the denominator. So that's where the form n minus 1 over s times s squared over chi squared comes from. That's where that comes from. Now, why is it that the left side of the interval is based off of the upper bound critical value, but the right endpoint of the confidence interval is based off of the lower bound critical value? Well, it has to do with the fact that we're dividing by chi squared. Remember that the upper bound is always going to be bigger because it's further to the right. It's always going to be bigger than the lower bound. Well, think about it in terms of a fraction then. In a fraction, if the value you divide by is bigger, as opposed to here where the value you divide by is smaller, isn't dividing by a smaller number going to result in a larger final value? That is to say, if you take something and split it and divide it by 2, as opposed to dividing it by 10, you get a bigger result. Now, that being said, you don't have to necessarily remember which one goes on which side. You're going to be calculating both of these values. It will be obvious which one comes out bigger and which one comes out smaller. So let's look at an actual example here. So let's suppose we randomly select and weigh 22 samples of an allergy medication, and we find the sample standard deviation to be 1.20 milligrams. Assuming the weights are normally distributed, construct a 99% confidence interval. Oh, excuse me, that should be 98%. A 98% confidence interval for the population standard deviation. So let's take a look at this. First of all, let's note the information that we're given. We are told the sample size is 22, which then leads us to the degrees of freedom being one less than that, 21. We are also told the confidence level is 98%, 0.98, which leads to an alpha value of 0.02, and therefore an alpha over 2, the area in each tail, as 0.01. So again, just because the visual aid does help, we'll draw a rough chi-squared distribution here, where again, we've got our chi-squared sub L with 0.01 area to the left of it. Over here, we've got our chi-squared sub U with 0.98 in the middle and 0.01 in the right tail. So we've got our degrees of freedom is 21. Oh, excuse me, I meant to do the highlighter. And we've got our, based on our alpha value and our confidence level, we've got that the area to the left to the right of our left critical value is 0.99, and our area to the right of our upper critical value is 0.01. And from there, we go to our table. So I'm going to scoot back here. Now, we're using the same confidence level as in the previous example, so that's good. But we have a new degrees of freedom. This time, the degrees of freedom is 21, which means we're looking at these values here, specifically 8.897 and 38.932. All right, so now we've got all of the bits that we need in order to come up with our confidence interval. So based on our two critical values, we need to do two calculations. We need to do n minus 1 times s squared over chi squared sub u, and the same thing over chi squared sub L. So, n minus 1 is our degrees of freedom. That's 21. The standard deviation is given to us in the problem. It's 1.20. Now we need to square it. Now, here's the tricky part. The square on this chi-squared is not an operation. It's not telling you that we need to square that value. The square is part of the variable. So what's going to go down here is simply the critical value, 38.932. That's it. We're not going to be squaring the denominator. That's an easy mistake to make. So be careful with that. But we put that all in the calculator, and what we get out of it is 0.7767 blah, blah, blah. Now, the sample standard deviation was done to 2 decimal places, 1.20, so we'll do this to 3. Now, for the other side of the confidence interval, we need to use the other critical value. So the numerator is going to, if you look at these, the numerator is the same. It's 21 times 1.20 squared. The difference then is in the denominator. And you can see here that the denominator of the first calculation we did was 38.932. That's fairly large. This time it's 8.897. That's definitely smaller. And as it turns out, we come out with, because we're dividing by a smaller number, we come out with a larger value here. So what we can see is that, yes, when we divide by the larger critical value, we get a smaller value at the end. And when we divide by the bigger, or the smaller critical value, we get a bigger result. But regardless, we have to do this calculation with each of the 2 critical values. We get these 2 values, and from there, it's obvious which one is the smaller one. Our confidence interval is that we are 98% confident that the sample variance is between these values. Yes, that is still the variance. If we want the standard deviation, we need to square root each of those. So if we throw a square root over each of those values, that'll get us to the confidence interval for the standard deviation. Here we get 0.881 is less than sigma. And for the other, we get 1.843. And that is our confidence interval for the standard deviation sigma. So definitely some differences here. No margin of error. We go directly from the critical values directly to the left and right endpoints of the interval. We are using the chi-square distribution, which is not symmetric, and that requires us to find the left and right critical values separately. And we should be aware of the fact that they will come out with 2 very disparate values that don't seem to be connected in any way. This is based, again, on degrees of freedom. And then the last thing, at the end of it all, we need to remember to square root those values that we get. Otherwise, you're giving a confidence interval for the variance. You need to remember to do that square root at the end. It's a very commonly forgotten thing when finding the standard deviation, and it's very commonly forgotten when you are finding the confidence interval for the standard deviation. So make sure that you remember that square root at the end.